This again will be a continuation of what we started. So we had started probability. Okay, so in this we touched a lot of concepts. So we are basically reading about prerequisites of probability. What are the prerequisites? What should I do before doing probability? So if you see in the previous classes, we saw different problems. We handled, let's suppose, Faraday paradox, and then we saw Monty Hall problem and some stuff like that. So the one thing that was constant, that there are experiments which you can repeat. So for which I said you can have frequent test approach. So where you have an experiment, you can repeat it. So many of the times, what the things that came up was counting. So you have to count things a lot. Okay, because frequent test approach tells you that number of favorable events divided by number of total events. So anything that you have to do with the number is basically counting. You have to count. Then I said that we have a different field in computer science mathematics called discrete mathematics. That's called as combinatorics, in which we learn to count. So we have a field, combinatorics. So in this field, what we basically do is you count without enumeration. So what is without enumeration? Basically, if I give you something, you don't enumerate all possibilities. Okay, I think we did an exercise like this also. I told you, let's suppose if I have ABC, so how many three-digit or how many three-letter words can I make out of this, which are different, and repetition is also allowed. So you could even if repetition is not allowed or is allowed, so you take different approach. So you can enumerate it. That's one possibility, you can enumerate it. But sometimes we don't actually want to enumerate, so you just want the number. You just want the number. If you want the number, then this combinatorics is very much useful. So if you, because of the frequent test approach, you have to count a lot. And I'll say in your probability journey, most of the times whenever you are using the frequent approach, so you will resort to counting. You have to count certain things. Okay, and today we'll handle this prerequisite. We'll see what is there in counting. The first thing is I'll teach you as just a set of rules. I'll tell you there are different rules to this, and based on which this counting is, whole of the counting basically depends on them. Okay, you have to only sort of understand them. Do not memorize them. If you understand these rules, the rules that I'm going to tell you, if you understand these rules somehow, and if you could say, let's say if I give you a situation, you could break down, okay, which rule should I use and why should I use this rule. So you are good to go with combinatorics. You don't need to learn much, but this can get very complicated. So that's why I'm saying you should not just mug it up. You should not just memorize it. You should basically understand it. Okay, the first rule that we'll go with is called as basic principle of counting. That's called basic principle of counting or multiplication rule. Basic principle of counting. Okay, or multiplication rule. Yeah, what is this all about? So let's suppose you are doing some task. Okay, you are doing a task. Call it task. If this task can be subdivided, if this can be subdivided like this, T1, T2, T3, something like this, and you have task, and then you can subdivide into subtasks. So in order to achieve this whole task, let's call it capital T, this task. What you should do, you should do T1 and T2 and T3. So you should do this and that. You should do all of these tasks, and then we can call that the task T has been done. Okay, so that's where multiplication rules come into the picture. So I'll tell you an example. We'll start with an example, a very basic example, which you might find in books as well. So if you, let's suppose, you have 3 shirts and you have 2 pair of pants, okay, and 4 pair of shoes. 4 pair of shoes. Let's not consider pair. Let's consider two pants only. 2 pants. Now sometimes you are in a situation that how many different outfits can we create? So how many different outfits can we create? If you see this problem is this. So the task is, this is our task T over here. So this is task T. The task is subdivided now. You have to choose a shirt and a pant and a pair of shoes. Okay, this is task T1, this is task T2, and this is our task T3. So what I had task, and then I have subtasks, which once I do all of these subtasks, I should do all of them. I should do T1 and T2 and T3. Okay, then how many outfits are possible? So simply what we can do is, you have three possibilities of shirts. Let's suppose I'll write these shirts down. So I have shirts S1, S2 and S3. Okay, then what I have is, I have two pair of pants. I have two pants. Let's call them P1 and P2. P1 and P2. Okay, then I have four pairs of shoes. Then each pair, let's call them S1, S2, S3 and S4, something like this. Why am I writing in this format is, you can see the first thing that you can do is, you can have the shirt 1 and this can be worn with this pant 1. Okay, and then this can be worn with the shirt S1. This is one pair. Or you can take it from there as with S2 or with S3 or with S4, something like this. And all of these things can be seen. Like this is called a sequential method, because you are following a sequence. You chose S1, then you chose P1, then you chose let's suppose S1. I'll write dashes over there so that I'll remove the repetition. S1 dash, S2 dash, S3 dash and S4 dash. This is one possibility over here. And again, you can have S1 with this S1, you can have this S2, then we can have S1 P2, then with this S1 dash, S2 dash, S3 dash, S4 dash, something like this. Okay, with this P2. So if you see, with only one shirt, this can be paired up with two pants, and this can be paired up with four pairs of shoes. So now if you just for this shirt, so how many possibilities are there? How many possibilities are there? So for each of these, if you again subdivide the task, you can see for each of the pant I have four possibilities. I have four possibilities for each of the pants. So for two pants I have 8 possibilities. Okay, and with one shirt, that means I have total 8 possibilities in here. I have to do with this with 3 shirts. That means I have 24 possibilities. Okay, everybody following me? So what I said is, if you fix this shirt one, if you fix this S1, you fix the shirt. Now with this shirt, you have 2 possibilities. You can wear 2 pants. Okay, so this will make, let's suppose now you just focus on one pant. If you fix this pant now, okay, you have 4 pairs of shoes. Now with this S1 P1, you have four possibilities to just wear shoes. And now you can span to P1 and P2. So with this, you have 8 possibilities, because you have 2 pairs of this. So for each S1, you have 8 possibilities. You have 8 outfits for each of these shirts. Now you have total 3 shirts. So how many possibilities are there? 24 possibilities. Okay, so if you understood in this way, then I can directly write the rule. So what the rule says is, this is 3 multiplied by 2 multiplied by 4, because number of shirts, number of pants and number of pairs of shoes. Okay, this is 3 into 2 is 6, 6 into 2 is 24. So what this rule says, formula is, so if there are multiple steps in the process which I just described, and each step has certain number of possible outcomes. So you have certain number of possible outcomes. So this was step 1, a task 1, task 2, task 3, and each has certain number of possible outcomes. The total number of possible outcomes will be, you just multiply them. Okay, you have to multiply them. So let's suppose in first task 1, it had R1 steps. This had R1 possible outcomes. Task 2, let's suppose, had R2, and so on. If this task is broken down till task n, so you had Rn steps. So this is total task T. Okay, so if this many outcomes are there, so what is this rule saying? This rule is saying that the total outcomes is R1 multiplied by R2 and so on multiply R1, and I can write it like this: pi I goes from 1 to n R of I. Okay, this is what this rule says. Okay, let's do an example again. So now let's say there is a license plate. You have to construct a license plate. Be active with this so that you also respond to me. I'll feel that this is an interactive session, not just I'm speaking. So you have to construct a license plate now. So now license plate actually has 3 letters. So you have 3 letters to take, and which is followed by 2 digits. So you have 3 letters and 2 digits. Okay, so the question is, how many possible number plates can be made? Okay, so this, if you consider this task T is making of a license plate. And now the thing is, the first task T1 is, you have to take 3 letters. You have to make a 3 letter, you have to make this license plate. The first 3 places should have the 3 letters of English alphabet. And then in here, after this, you have to have 2 digits. Okay, so let's suppose you have 26 letters and digits are from 0 to 9. Okay, so can you answer this now? If you see this task T1, how many ways can I do it? So for this, I can choose 26 letters. So I can break this down into 3 subtasks. Okay, this can be again broken down into 3 subtasks: T1 1, T1 2, T1 3. The first subtask would be to choose the first letter. How many possibilities are there? There are 26 possibilities for this, and there are 26 possibilities for this also. 26 possibilities for this also, because repetition doesn't matter to us here. So you can repeat as many number of times as you want. Okay, so this T1, this actually has, this T1 task can be done into 26 cube ways. Then this again, if you see, you can break it down into two subtasks. So this is T2, our T2 is this, so we can break it down T2 1, T2 2. So selection of first digit, how many numbers we have? We have 10 numbers, and this can be done in 10 square ways. This T2 can be done in 10 square ways. Now in order to combine this together, so what you can do is you can say T1 and T2, combine them together. So the total task can be done in 26 cube multiplied by 20, these many number of ways you can construct the number plate. Okay, but there is a note that you should take here. So what I'm telling you, where you cannot use this multiplication rule. So let's suppose you are in, say, some city A, and there is a city B, and there is a city C. Let's call it D, call it S. So this is your source city, and this B is intermediate city, and this is the destination city. So let's suppose there are a couple of roads. So you can go via here, you can go like this, and you can go like this also. You can go like this, and you can go like, let's suppose this also. Okay, if you see this, you just add one more. So from S to B, you have 4 possibilities that you can take. Okay, and then from B to D, you have 4. Here you have 3 possibilities. Here you have 4 possibilities. Now you can directly say, so how many number of possible routes are there, so that you can reach from S to D. You can directly say 3 multiplied by 12. 3 multiplied by 4 is 12. Okay. So now the problem might go like this. Let's suppose for each of this route, once you reach B, you can take all of these routes. But sometimes in real world, what might happen is that if you take this route, if you take, let's suppose, this route, you are restricted to you can only take these 2 routes, let's suppose. Now you cannot use multiplication rule. Why? Because initially what we're assuming that if we somehow reach B, so from B we can take all the 4 routes. But if you see in the real world, what happens sometimes, if you take one route, you cannot take all of these routes. Then you are restricted to use, let's suppose, if you take this route, so you can, let's suppose, take these 3 routes. If you take this route, you can take, let's suppose, all of these routes. Now the formula doesn't go like this. You cannot directly say 3 multiplied by 4 is 12. So this is product rule, and this is the number of outcomes. So what you should now do is you should actually break it down now. So you will break it down. How? For the first route, I have how many? 2 possibilities plus. For the second, I have 3 possibilities. So this was my task T1, and this was my task T2. But in T1, if you see, so it was subtask. So if I choose one route, so T11, T12, and T13, I had 3 tasks that I can do. Okay, let's call them as N1, or let's suppose T1, this is all right. So if when we have this T2, so in this T2, if you see this, so if you choose this route, so you are now you can only choose now 2 routes over here. You can choose 3 over here, you can choose 4 over here. Now what you have to do, you'll add these things up. You'll say 2 plus 3 plus 4. So this is 9. These many routes. Now you cannot apply directly the multiplication. You have to be very careful once you are using this multiplication rule. So to summarize it, what I was saying is, so let's suppose you are going from somewhere, you have in this experiment T1 and you have experiment T2. So let's suppose you have this N1, N2, N3, N4, something like this. Okay, till let's suppose NM. So if all of these have same possibilities, if all of this has, let's suppose here they have 4 possibilities, here also they have 4 possibilities, here also they have 4 possibilities. Now the total possibility, if you see the M, and if all of these, let's suppose, consider them N, then you can write M into N directly. But what if some of the possibilities, let's suppose one of these, if one of these has only, let's suppose, K possibilities. So what you can do is you can say M multiplied by N minus 1, because only M minus 1 multiplied by N, because only these many number of things till here had N possibilities, last had K possibilities, so you will have to add it. So you have to be careful in such scenarios. You don't have to directly use product rule. Okay, this is one thing that I want you guys to know. Okay, are you following me? What am I saying? Okay, so this is one of the rules, which is called as the name we have given it is basic principle of counting, which is called as the multiplication rule. Let's do something with it so that you have a good understanding of the rule. Give me a second. Let me give you a question. So the question goes like this. So you have to form a password. So I'll take your questions after this. If you have to form a password, so now password, what is it? The password is let's suppose 6. It has 6 places. I'll say 1, 2, 3, 4, 5, and 6. Okay. So if you have this sort of thing, so you want to construct a password. So the allowed things are A to Z, small case, caps A to Z, 0 to 9, let's suppose. Okay, so tell me how many passwords can you make? Okay, this is the question to you. Okay, so the total number is 62 here, because 26 of these, that's 52, plus this 10, that's 62, and each of this place can take any of the values from here. So we are giving 62. This is our task. So this is our T1, T2, T3, T4, and T6. So each of the tasks has how many possibilities? 62 possibilities, and then we'll just multiply them together. Okay. One more question can be like this. You are designing a test, let's suppose. So you are designing a test, in that you have to have two difficult questions. So you have two difficult questions. So three questions are three types of question can be MCQ, short answer essay, and 4 topic wise questions. Okay, so these are the possibilities. So you have to select, so how many ways can you select a test? So there is this difficult level, and then you can select this 3 types of questions, which are either MCQ, short, or essay type. These are 4 types of questions, and then you have 4 topic wise questions. Oh, oops. Okay, so what can you do if you want to take a test? So you can mix them. If you want to take this question and you want to take each one question from each of this, so how many possible papers can you make? So as known that this is task T1, task T2, and task T3. So now we have T1 multiplied by T2 multiplied by T3. Okay, whatever is the number is your answer. Okay, now this is the basic rule of basic principle of counting. This is called as the product rule. Now we'll move on to the addition rule. Okay, or sum rule, it's called as addition principle or sum rule. Addition principle or sum rule. Yes, question. Let's go to this second rule, which is called the addition principle or sum rule. So what this basically states is, the first thing that you should sort of know here is, whatever events are happening, they should be mutually exclusive. That is, they should not have anything which is present in both the things. So let's suppose you have some event. You have this task again now. So you have this task. So now you break this task into T1, T2. So if you do T1 or T2, you can consider your task done. So you can do either T1 or you can do T2. Okay, let's consider an example so that this becomes more clear. So let's suppose you are choosing a dessert. You are going to a restaurant and you are thinking that I want to have some dessert. So in that dessert, you might be given multiple options. You might have 5 types of cakes. Okay, or you might have 3 types of ice creams. You might have 2 types of pastries. So all of these are dessert foods. So if you just choose one of them, so what will happen is the task will be done. So here, if you see, the task is being broken down into T1, T2, and T3. But now if you see this, how is it different from product rule? So here, in order to say that task is done, you don't have to do all the tasks. You can do one of them. If you do one of them, you are considering your task to be done. You are saying, okay, I am done with this. So, but if you see, one more thing that you can see over here is, these tasks don't have an overlap. Okay, so 5 cakes, I can write cake 1, cake 2, cake 3, cake 4, and cake 5. I can write ice cream 1, ice cream 2, and ice cream 3. I can write pastry 1, pastry 2, and pastry, only 2 pastries. So nothing has an overlap. If you consider this as set, and if you consider this as set, if you consider all of these as sets, so they don't have an overlap. So they are disjoint sets. Or if you say, if this thing happened, so this is considered an event happened. So all of these are mutually exclusive. Okay, so events that they cannot happen together. So that's what was the meaning of mutually exclusive event. So we'll go into probability once I touch that mutually exclusive. What's the meaning of an event experiment? But here, to get this point through, you consider this. If you choose a cake, you cannot choose an ice cream. If you choose an ice cream, you cannot choose the pastry and the cake. The other two, you cannot do it. So all of these things cannot happen simultaneously. That's what I mean by mutually exclusiveness. Here, if you see this, in order to consider this task to be done, you have to either do T1 or T2 or T3. Okay, you have to do one of them. So if you have done one of them, so you consider your task to be done. Like the thing was, the question that was, how many ways can you select a dessert? So how many ways can you select? You can choose any cake among the 5 cakes. You can choose any ice cream among the 3 ice cream. You can choose any pastry among the 3 pastries. But these are mutually exclusive. They are disjoint sets. Okay. So what you do is, you now just add these things up. So you can choose 5 types of ice cream. So there are 5 options. You can have 3 types. You can have 5 cakes, 3 ice creams, and 2 pastries. So 5 plus 3 plus 2. These are the number of options you have. So you have in total 10 options or 10 outcomes. 10 possible desserts can be there. So what does addition rule say? So this addition rule states that if there are multiple mutually exclusive events. Okay, and the total number of outcomes then is just the sum of the outcomes of these individual things. So you have this event 1, or which are called as task 1, task 2, task 3, and task n. So if each has possibility, this has R1, R2, consider this as Rn. So if they are mutually exclusive, and now you should see that once I do task any of these subtasks, so the task is considered as done. So the total number of outcomes possible will be R1 plus R2 till Rn, or summation of I goes from 1 to n Ri. Okay, so this is the addition rule. As I said, let's suppose you have this choosing as desert, or again you can have if you have to travel from city A to city B. Let's suppose again the city example. If you have to travel from city source to destination, so let's suppose you have different routes. You have 4 different bus routes. You can take a bus which has 4 different routes by bus, and then you have 3 different train routes. Okay, and you have 2 different flight routes. So how many possible routes are there? So you can either go by a bus transport, or the train, or the flight. I'm not saying you can mix them up. So this is total. I'm keeping them mutually exclusive. So this is 4 plus 3 plus 2. This is equal to 7, 9. So this is equal to 9. These many number of possibilities are there. Okay, I hope that this addition rule is not that difficult. But one caveat here is that they should not have overlap. So let's suppose if I tell you this, if I say, let's suppose that something happened which is 1, 2, 3, and 4, or something like this, 5. Other thing happened in which I had 9, 10, 11, 12 something, and 4 is also there. Now here you cannot apply the summation rule, cannot reuse this directly, because now you're over counting things. So you counted this 4 twice. You counted this in the first event as well, because these things are not mutually exclusive. Okay, they are not disjoint sets if you see them. Okay, so if this thing happened, I cannot say that this is not happening. So if this 4 happened, that means both of these things happened. So these events are not mutually exclusive. So they can happen simultaneously. If this 4 happened, that means E1 also happened, E2 also happened, because 4 happened, because 4 was common in both the things. So you cannot apply the summation rule over here. Any questions on summation rule? Okay, let's maybe do some examples of the summation rule, if I have some basic examples. Let's say you have to select a price. Quite easy. I'm taking very easy problems, and then I'll mix them up. Okay, let's suppose you have to select a price. If you have to select a price, and there are options. You have 7 books. Okay, and you have 4 gift cards, and then you have 3 gadgets. Okay, so how many ways are there in which you can give a price? So now you can give only one. If you give a book, that will be considered price ceremony will be done. So now you have 7 possibilities from books, you have 4 possibilities from gift cards, you have 3 possibilities from gadgets. So in total you have 14 of these possibilities in which you can distribute the price. Okay, now comes the caveat in both of these. Now if we, let's suppose, have this, if we have events where there is overlap, if we have an overlap of that sort, if we now have overlap, so what can we do? Okay, now before that, let's maybe level it up a bit, and then we'll land it to that. Let's suppose now I'll give you a question about bit strings. Say I have to construct a, let's suppose I have 5 places. So I'm only allowed to use 1 and 0. Okay, so these are my binary digits. So how many possible number of bit strings are there if I have these 5 places? 1, 2, 3, 4, and 5. So how many number of possibilities are there? Total of possibilities are 2 to the power, because you can have this 2 possibilities, or 2 possibilities here, 2 possibilities, 2 and 2. So this is 2 to the power 5 possibilities. So what if I tell you, let's suppose, how many possibilities are there if I just fix the first 2 bits? I am giving 1, 0 as first bit. How many possibilities are there? So how many possible bit strings are there which start with 1, 0? So how many possibilities are there? So pretty easy, 2 to the power 3, because you now gave 1, 0 to the first. And what if I say this? How many possibilities are there if they end with, let's suppose, 0, 0? If they end with 0, 0, again 2 to the power 3 possibilities. I hope everybody will follow this. So you have this 2 to the power 5 when you were giving whole thing. Now if we fix 2 digits that are at the initial stage, so you are saying 2 to the power 3 because we have 3 places to fill. Same thing goes here over here. So now if I combine both of these two, so I am saying now the strings can be, these bit strings can be either of this form, or they can be either of this form. So now tell me how many number of how many number of bit strings can be there? How many number of bit strings? It can be either of this or of this. Okay, now you can see that which rule to apply. Do you want to use product rule or do you want to use summation rule? So I told you upfront. So whenever you see this or thing, so the point is what you should do over here is, okay, you should see if there is some overlap. Now these things are not mutually exclusive. So if let's suppose this string came up, this falls into this as well as this. Okay, so because these events are not mutually exclusive, there is an overlap. So what you should do now, you have 2 to the power 3 possibilities initially, then you have 2 to the power 3 possibilities from this task. Now you have to reduce, you have to, because you overcounted. Let's consider these are two sets like this. Okay, let's consider this with 1 0, starting 1 0 and ending with 0 0. So you had 2 to the power 3 possibilities here, 2 to the power 3 possibilities here. But if you see, you counted this overlap portion twice, once with this and once with this. That's why we have to subtract it once. Okay, we have to subtract it. So how to find that? What is the common strings they have? They have 1 0 and then dash and then 0 and 0. So here there are two possibilities. Okay, so the common strings are two common strings. So total strings are 2 cube plus 2 cube but minus 2. So this over here, if you see, is our number of, let's suppose in event 1 or task 1. So number in task 2. So this is the overlap which we said this is called as intersection. So I can write it number of E1 intersection E2. This is the overlap and you have to remove the overlap. So that's why you have to be careful. You have to be careful. Once you see these, don't directly jump with the answer. So you should see the rules. In the product rule, the caution is that once you have each step you should check that the next step, does it have all the possible outcomes associated with it. If it does not have, then you cannot directly use product rule. Same thing goes for the sum rule. For the summation rule, when you see some of these events happening, so if there is an overlap, you should subtract that overlap. Okay, so this leads us to the third principle, which is called as exclusion inclusion principle. Let's go to that. The same thing if you see it over here. So if you have these events which I said, so this is the inclusion exclusion rule. So let's say you had 1 and 2 events. So you had this event and this event. Okay, now if you have to count, so this had number of A and this is number of B element, and then the intersection is, and so this over here is number A intersection B, something like this. So if I have to count the possibilities, okay, if I have to say number of A union B, so how much number of elements are there which are in this, but I should not over count. So what I will do is I'll say number of A plus number of B, but because of this got over counted, this portion, so I'll subtract it once. I'll say number of A union B, A intersection B, sorry. Okay, so usually how do we write it? So instead of this number, we write it cardinality like this, A of B. So this means number of elements is equal number of elements of A, number of elements of B subtracted by number of elements by A intersection B. Okay, now let's go to the three events. If 3 events are there which are not mutually exclusive, like this and this and this, okay, something like this. So this is our A, B and C. So how I can write this? How can I write A union B union C? This means number of elements in A union number of elements B, number of elements C. So if I put them all together, so how many elements will I get? So I'll initially take all the elements of A plus all the elements of B plus all the elements of C. Okay, I took all of A, all of B and all of C. If you see, I took all of this and all of this. Okay, I took A, B and C. Now if you see, there is an overlap. Once I took this A, I took this portion. Okay, once I took B, I again took this portion. Okay, so I have to subtract it. I have to subtract it once. So I'll say minus A intersection B, because I have to subtract it once. Once I took this A, once I took this C, again I have to I overcounted this portion. How many times I overcounted it? I counted it twice. I should have just counted once, so I have to reduce A intersection C. Same thing goes with A. Once I had with this B and C, so once I had this B and C, I overcounted this portion. Okay, it was taken twice, once with C and with B, so we'll subtract it once. So A C intersection of B intersection C, so you are subtracting this. So now if you see what happened as a result of this, so as a result of this, what happened, there was this common portion. It was initially taken with A, it was initially taken with B, it was initially taken with C. Once I counted this and this. Okay, so I did it. So I counted it how many times? I counted it thrice, let's suppose. So I counted this portion, let's suppose, this portion, this. So once I subtracted it again, I subtracted it from here because intersection, it comes also in intersection. So I subtracted thrice also. So I counted it thrice first and then I subtracted it thrice. Okay, but now I at least have to include it one time. So now if you see till this, we have not included this portion now because I initially overcounted it. I overcounted 3 times. Then while I was subtracting the intersection part, I overcounted it again 3 times. So what I did is I said 3 initially minus 3, so it gives me 0. So now basically I did not take it into the number of elements. So that's why I should add at the end, I should add A intersection B intersection C. So for how many of you is this clear? Okay, I hope this is clear for everyone. So you can see what, that's why it's called inclusion exclusion. Why? Because let's suppose you include this, then you exclude this, then you again include this. So if it's for 4 sets, so the same thing process. You include, exclude, include, exclude. The single terms you will add, double terms you will subtract, and let's suppose triple terms you will add, and then 4 terms you will again subtract. Something like this. It'll go on in that format. Okay. Let's now do a question on based on this so that we'll have a bit of practice. Let's say you have a library. In that library, you have 100 fiction books. 100 fiction books. And you have 80 history books. And you have 30 books in which are fiction and history. Okay. So how many total unique books do you have? You should not directly now go to the formulation. Okay, that means number of A is 100 plus this 80 minus this 30 is equal to 150. You should reason it from first principle so that you understand it. Okay, I don't want you to mug up. Okay, let's go to the more interesting case. Let's suppose you have 50 students who are learning Spanish. Okay, and then you have 40 students for learning French. And then you have 30 students for learning German. And then you have 10 students who are learning Spanish and French. And then you have 5 students who are learning French and German. And then you have 8 students who are learning Spanish and German. Okay, and 3 of them are learning all the languages. Okay, now tell me how many unique students are there? How many total students? Total or unique students in this case? If you see this, so now what we have is we have 3 things: Spanish, French, or German. Okay, and other things are overlapped. The first thing is you have these tasks. This is consider this as S, this is our F, and this is our G, German. Okay, now what you can see is number of people who speak Spanish is, let's suppose, 50 plus number of people who speak French is 40, number of people who speak German is 30. But we know that there is an overlap. Okay, there's a lot of overlap. So what overlap is there? First, if you see these 3 sets, 1, 2, and 3, this is how you should reason while doing such things. This was our Spanish, this was French, and this was German. Okay, so tell me the overlap. So what is the overlap? The first overlap is between S and F, between Spanish and French. So that I should subtract. So what should I subtract then?
10.
Give me a second. What happened to this? Okay, if I subtract, let's suppose 10, because that is the overlap between this S and F, Spanish and French. So if I'm having overlap between this F and G also, so what should I subtract? Should I subtract or should I add it? Because I overcounted it, minus. And then what more should I subtract? The people who speak Spanish as well as German, that is 8. Then the problem is because this was the overlap between all of these things. Initially I counted it thrice, and I subtracted it thrice, so I am not basically counting it at all now. So that's why I should add it one time. So plus this, these speak all of these things. So this actually comes out to 100. This comes out as 100. So what if I did like this? Sometimes it might happen like this, this, and now you would have overlap, something like this. You have this A, you have B, and you have C. If somebody tells you, okay, now tell me the total outcome, total possible outcome. So here it is A plus B plus C. Okay, because I am counting this A whole, then B whole, then C as a whole. Then what should I subtract? Should I subtract anything? Bamboo, should I subtract anything?
In this case, I think we should just subtract A under A intersection B.
Yes. because it was over counted. It was once counted with this, it was once counted with this, so we have to subtract it once. So we subtracted once, and the C had no overlap in anything, so you had some other rule now. Okay, it depends on how the question was formulated. So that's why I'm saying you should reason from first principles. Do not directly go, okay, here I'll apply the inclusion exclusion principle, here I'll apply, let's suppose, summation rule, here I'll apply product rule. Sometimes questions can be like this. You have to understand question and you have to break it down and accordingly adapt the rule that you have, because these are the general things. That's why in some rule we explicitly said if there is no overlap, if they are mutually exclusive events. So that's why you should take care of these things. Now, okay, I'll ask you a certain question. Let's suppose now what you have is you have two people. Let's say now you can mute yourself now. So let's suppose you have Fahad and Asif. Okay, let's say Fahad and Asif are starting some company together. So they have possibility that there are 10 offices in a building. There are 10 offices in a building. There are 10 offices in the building. So what I want is I want to give them two separate offices. So how many possible offices can I give? How many possible ways can I give them these two offices? Okay, we have two people, you have 10 offices. Now you have to allocate them two different offices. So how many possible ways are there in which I can allocate them these two different offices? The problem at here is, let's suppose we have 10 offices. So the approach, I'm telling you, why is it correct? You have to find a mistake in the approach. I'm saying there are these offices. So there are these 10 offices. So each office has a possibility. Then either Fahad will go in or Asif will go in, or it will remain empty. I'm saying that there are three possibilities for each of the office. For each of the 10 offices, there are three possibilities. Okay. So what is the problem with the approach? Yes, go ahead.
The problem with the approach is this approach assumes that either Fahad or Asif can have multiple offices. They cannot have multiple offices. This problem can be rephrased in such a way. Each room has three possibilities: Fahad, Asif, or empty. But in the end, 8 rooms should be empty.
Right. Right. So how can you approach that in that scenario? How can you approach it? Can you do it with this also? So does it follow any rule? You can say that you have three possibilities for each of the room, but at the end you would have 8 empty rooms, and 2 of the rooms should have Fahad and Asif.
Okay, one room should have Fahad, one room should have Asif,
yes.
and 8 rooms should be empty.
Yes. So out of these 10 rooms, how many possible ways can you keep 8 offices empty? So how many possible ways are there in which you can keep 8 rooms empty? You basically have to just choose 2 rooms. How many possible ways are there in which you can just choose 2 rooms? That is the problem. Basically, the problem basically boils down to out of these 10 rooms, you have to choose 8 rooms. Okay, 8 rooms, keep them empty, and then 2 rooms you can keep. Let's suppose for Fahad and Asif. So if I use this approach, the problem with this approach is, so this assumes that either Fahad will go in or Asif, or this will be empty. Okay, so it can lead to the possibility I can leave all the things empty, or I can have Fahad at multiple places, or I can have Asif at multiple places, something like this. Okay, so this approach is wrong in that way. The second thing that we phrased it, okay, now can we rephrase the problem? The problem was rephrased like this. So if you have 10 rooms, so you have to select out of these 10 rooms, you have to select only 2 rooms in which Asif and Fahad will go, and how many possibilities are there in which I can select 2 rooms. Okay, something like that. And if this approach is wrong, why is it wrong? If it is correct, why is it correct? Okay, this intuitively seems correct. Okay, they're looking at the problem. That's what I said. In probability, the modeling matters a lot. Okay, once you model a problem, you can have 2 different models and they look equally same. They look equally, no, there is nothing wrong with them, but they give very different answers. Okay, and then you have to reason why is one modeling correct and why is this wrong. And this we'll do in the initial starting the probability once we go to the modeling of the probability problem. So once I give you the problem and I'll tell you, okay, make a sample space out of this. So you should see all the possibilities and you should know how to reason. Okay, what is wrong here? So as Fahad rightly mentioned over here, that there was a lot of wrong things that I did. Okay, let's suppose I did this approach now. So okay, I have to think it through. Okay, is it correct? Is it wrong? So modeling matters a lot. That's what I said. So modeling or approach, this matters a lot. Sometimes an approach can seem, okay, there is nothing wrong with this approach, but if you take another approach, you'll see, okay, there is nothing wrong with this approach also. So these can give very separate answers. Okay, then you will have to see, okay, which one is correct or both are wrong. So you'll have to learn to reason about these things. Okay, I hope that you at least got an understanding what I meant by introducing this problem. There can be different ways in which one problem can be thought of. So you have to see which is the right approach. Is there let's say I have say 58 cars or something like, oops, give me a second. Say I have 58 cars. Okay, so I have these 58 cars. So in how many possible ways can I, let's suppose, put them in a line? Okay, in how many ways? In how many ways can I put them in? Let's suppose I am trying to make, yes, go ahead.
Identify two different
Yeah,
cars.
different. Assume that they are different cars, they are different color, different models. So each of the car, they are not identical. Not identical. Good question. These are the things that you should that should come into your mind. Oh, are the same? Then the arrangement will differ. So they're identical cars.
In that case, the answer would be 58 factorial.
Yes, 58 factorial. Okay, that's where I wanted to actually introduce you to the factorial. So the possible actual answer would be 58 cross 57. Okay, cross this till a 1. Okay, because I have 58 places and I have 58 cars and I have to put them in a row. So this is what is defined as 58 factorial. And it is a very neat way to put it. Okay, now let's suppose if you have this, if you now let's say if you want to have an arrangement of this, but they must be in some specific order. That's why we use these the permutations. So from the factorial we'll go to permutations, and from the permutations we'll go to combinations. Now the thing is, if you have an arrangement of the objects in which this order matters, okay, in which the order matters, okay, then what you basically use is you resort to permutations. I don't want to go to the formula directly, we'll see it, and then you should be able to reason it from the first principles. Okay, let's say we have this. So we have let's suppose A, B and C are there. So these are to be arranged. Okay, they are to be arranged like this. So how many ways are there in which I can arrange these?
Sir, can you repeat the question? We have 3 empty places and we have 3
we have 3 objects. We have 3 places A, B, C, and we have these 3 letters, and we have 3 places to put them. So how many ways can the letters A, B, C be arranged in, let's suppose, these 3 in these 3 places?
3 factorial.
Okay, 3, 2 and 1. If I just keep it 2 places, what will it be now?
It would be 3 C2.
3 multiplied by 2. Let's suppose if I have A, B, C, D and E, so I have to put them in, let's suppose, 3 places. So what will be the answer now?
5P.
5?
5P2. 5P2. 5 4 into 3. 5 into 4 into 3.
5 into 4 into 3. Okay.
Yes.
I don't want to directly tell me the formula, because I want you to reason from, okay, why is this P defined the way it is? Okay. Now if you see this 5 into 4 into 3, if I could somehow write it like this, 5 into 4 into 3 into 2 into 1, something like this. Okay. So this will be my 5 factorial. So this would be my 5 factorial. But the point is, I introduced these additional terms over here. So somehow I should get rid of them. So how to get rid of them? I should divide it by 2 multiplied by 1. Somehow like this. Okay, I added these terms and I also divided. So this is 5 factorial. So what I did is I divided by 2 factorial. So where this 2 actually came from? So that I have to see now. So I made this problem. So if I had these places like this, I had 3 places. So I said I can write it like 5 factorial divided by 2 factorial. And now if I can write it like this, so this is 5 factorial divided by 2 factorial. So where did this 2 came from? So actually I had only 3 places, 1, 2 and 3. I added 2 more places on my own. So what I said is, I said 5 and then subtract these 3 places which were filled. So I said 5 factorial divided by, actually I had 5 places, but subtract the places that actually I had. Okay, and I added the factorial of this. So this is 5 factorial divided by 2 factorial. So now if I generalize this problem, if let's suppose I have n possibilities, and the order matters to me, and I also only want to fill R things. Okay, I have these R things possible for me. So what I'll do is I'll fill all the n possibilities. So I'm doing all n possible, that is n factorial. But what I'm removing then is, because I have to only fill how many R possibilities. So I'll say n minus R factorial. That's what I said by this. So this over here is called as NPR. This is called as a permutation. Nothing to memorize. You should not memorize it at all. At any cost, you should not memorize it. Okay, why? Because if you go into the formulas, then you'll get confused. What thing do you? Should I use permutation or combination? And that is good, that works with competitive exams, but here we are not preparing for a competitive exam. What we are doing is we are basically learning the thinking process. So how should I go about it? So this permutation formula helps a lot, because now you don't have to go through all these things. So if I say order matters, you can directly use this, but this you should be able to reason from the first principles. Is it clear? So this is called a permutation. So what is a permutation? So permutation is an arrangement of an object in a specific order. The order selection matters in permutation. Okay, order selection matters. Order selection matters in permutation. Let's now consider this. Let's say you have 5 books. Okay, you have 5 books and you have to arrange them onto 3 shelves. Okay, so how many ways can you do it? So you have 5 books: book 1, book 2, book 3, book 4, and book 5. And you have to arrange them into 3 shelves, something like 1, 2, and 3. So how many possibilities are there? So how many ways can you do it? So on the first shelf, there are 5 possibilities. You can put 5 books. Once you exhaust that, the second book only has 4 possibilities, and the other book only has, and the other shelf only has 3 possibilities. Okay, so how to come with this? So we can write it 5 into 4 into 3 into 2 into 1. In order to remove this 2 into 1, you should basically divide by it. This is 5 factorial by 2 factorial. If you again do it, so 5 factorial divided by this is actually 5 minus 3 factorial. Okay, so if we consider these as n possibilities and this is r, so we had npr. So again we did n factorial divided by n minus r factorial. That's what we did over here. Okay, and now we'll move to the combination. So what is in the combination? In the combination, the selection of objects, the order does not matter here. So order does not matter. So what I said is order does not matter. So that is the combination. In the permutation, what we had is, in permutation, order mattered, okay, in which we took it, order mattered a lot, okay, in which shelf we are putting it. So here the order does not matter. Let's consider this. So you have a committee of people. You have to form a committee of people. So in this committee of people, 3 people have to be selected to choose a committee. Okay, now actually we had 5 people. We have 5 people. We have 5. We have 5 people in which a committee should be chosen, and you have to only choose 3 people. So you have 3 spots. Okay, but you have to only choose. You have to choose from 5 people. The 3 people for a committee. What you can do is, for the first place, what you can do is, you can, let's suppose, take you can say I'll take all of the 5, one of them, and then 4, and then the 3. Okay, have we over counted, under counted? What have we done? So in here, if you see, you also counted the order. You say in which order did I take it? Okay, if you see in that way, so you say, okay, in which order did I do? So in order to remove that order, so what should I do is, I should basically remove that, how many number of repetitions would be in the order. So it is like this. So if you have, let's say, ABC, so ABC is actually it can be considered as a combination. So if I say BCA, both these things are same in combination. So they are different permutations, but they are same combination. They are the same combination. So if I had this A, B, C, D, and E, let's consider these are 5 people. So now I have to choose 3 people among them. So this ABC and CBA or ACB, this is same committee. Nothing was done, because order does not matter. These are different permutations, but they are the same combinations. Okay, so how many of these things can you see it over here? For each of these things, because I am choosing 1, 2, and 3. So how many same things can you see? So can somebody guess how many same things can we see? Because this is the total number of people, this is the total number of ways I can choose it. But the number of repetitions, if you see it in each of these, how many repetitions are there? So there are 3 factorial repetitions. There are 6 repetitions. 3 factorial. Okay, these because in here we have different repetitions. So if you see, we got ABC. So in how many permutations can we arrange them? So this is 3 factorial. So that is 6 ways. So now for each of this, I have overcounted them these many number of times. So I should just consider them once. So don't you feel that we should divide it? So we should say 5 into 4 into 3 divided by 3 factorial. Okay, this division is basically just to remove that, because our order doesn't matter for us. Okay, now if you see, so this formula again, I can come out to permutations. I can say this is 5 factorial divided by 5 minus 3 factorial. But in here, an addition of 3 factorial came in. So this 3 factorial came in. Why? Because I somehow took that order into the consideration also. So now if you generalize it, say if you generalize it. So if you generalize this, so you had n people and you have to choose r from them. So you said I'll take it n factorial divided by n minus r factorial times. So this was permutation way. So the order matters here. In order to remove the effect of order, what you said I'll just divide it with the this r factorial. Okay, so this over here is called as NCR, written as like this or like this. This is combination. The difference between the permutation and combination, permutation in that order matters. So as I said, ABC and CBA, these are two different permutations. But in combination, they are the same combination. That's why it's named as combination and permutation. Permutation basically means different permutations, and combination basically means order does not matter here. So order matters and order does not matter. Where order does not matter, we call it a combination. So here we can say we are a combination of 5 people because order won't matter here. Okay, then this is called as permutation where the order matters. So now if we have to compete, I mean, let's suppose our class has 12 students. Okay, if I take an exam, let's suppose, and I'll give ranks based on the number. So how many permutations are possible? Now the question is not of the combination, because there's only one combination possible with the 12 people for the 12. Now if I have to rank them, so how many number of these things are possible? How many number of let's say these different ranks can I make, or they're called schedules? How many schedules can I make? So the simple thing is I have to give them 12 places. Okay, and the first place 12 students can come. Once he took the first place, so this is 12 factorial ways. So these many number of ways, because I have to select all of these things. If I have to say, okay, if I have only select top 3 students, 1, 2 and 3 out of these 12 students, so here how many number will this will be 12, this will be 11, and this will be 10. So this basically means 12 cross 3, 12 permutation of 3, because why order matters here. If I have to only give 3 places, okay, only 3 places, you will resort to permutation. But in the combination, if I have to choose a team among these, if I have to choose team of 3, okay, so team of 3 basically means the permutation should be removed now. So you should just resort to the combinations. Okay, now permutations is where order matters, and combination is where the order does not matter. You again count in the both the things. Okay, the simple formula is NPR is basically equal to n factorial divided by n minus r factorial. And you now know where this formula came from. And NCR basically means n factorial divided by n minus r factorial into r factorial. And you also know where this comes from. So this term here is because of order. Okay, and this thing here because we wanted to use factorial. Okay, that's where from these formulas came. Actually, these formulas were not necessary to make. We can directly done them. But at least now there were 2 things that we saw. We saw order matters. We saw here order does not matter. And what we came with the principle which is called as factorial. We said, okay, if something is repeating like this, 5 into 4 into 3 into, if we go backwards still 1, so we'll call it a factorial. So in order to use this concept now, factorial, and then we came up with these formulas. Okay, I hope that without the formulas you can still derive them. Now you saw that why do we come up with the formulas. So initially what mathematicians do is we come up with some symbols notations. So this notation was came up with factorial notation. Factorial means this, it was given a specific meaning. So factorial was given if we write 5 factorial, so we said 5 factorial means 5 into 4 into 3 into 2 into 1. It is the meaning of the factorial. Okay, and also 0 factorial is 1. Okay, this was considered 0 factorial is 1. So some things like that. And factorial is not defined for negative numbers. So all of these assumptions were made. And once we had the way of doing them, so we converted them into simpler formulas. But in the process, what people do is they'll remember the formula and they'll forget about the process. They'll see, oh, okay, this looks like a permutation question. This looks like a combination question. There is nothing permutation, no combination question. There is counting questions. You have to count certain stuff. But now you have to ask yourself, does the order matter? Yes, order matters. Does it make sense? Here order does not matter. So one thing you call permutation, one thing you call combination. So if you reason from first principles, so you should not get caught up in the lingo. Okay, if sometimes lingo is very thick, so that's what makes people scared of maths, because they sometimes get scared of the lingo. Oh, this is something permutations are common, even in the integrals. This is integral. It can be taught from the first principle, and then you just have to name it as we thought it. Okay, and we just named it as factorial. And after that, we had to name something permutation. We said, okay, can we reuse this factorial somewhere? So we reused it. We just manipulated it with here and there, and we came with permutations. What can we do with a combination? Combination is actually a permutation, but without order. Order should not matter. Now we just remove those number of things. So you should again do the same thing with all the mathematics. So one of the principles that I was telling you that I'll teach is that we will see everything from rediscovery point of view. Okay, that is the thing that I want you people to do. I cannot discover it myself. So how many among you are now feeling at least we could have came up with these permutation combination formulas ourselves if given time and if given the right process? Okay, and this is the goal of these classes. Okay, this is what makes these classes different, because I want you people to see it from a rediscovery point of view. If I come with a factorial, let's say if I did not define factorial, if I defined it in some other way, if I defined, let's suppose, factorial in some other way, let's suppose I have defined it as 5 something like this, 5 into 3 into 1, I just minus 1. If this is 5, let's say factorial dash, I defined it like this. So n factorial dash would be like n multiplied by n minus 2 multiplied by n minus 4, something like this. I just reduced by two things if I defined it like this. So can you again manipulate these formulas by just incorporating factorial dash? Now you don't have to incorporate factorial, you have to incorporate factorial dash in this. The thinking that I want you to know is, so once you decide on some convention, once you decide on some notation, then you respect the notation and accordingly come with the formulas. Okay, and formulas are not some magic pill where you go, oh, you have to just plug and put these values. So you come up with the notations, and in the notations, then you respect the notations and respect the assumptions, and then come up with these formulas. Okay, I hope if you have understood this NPR, the NCR, and if you have understood the principles of counting, you're good to go with counting. So this is all there is to learn about permutation and combination, I'll say. But there are a lot of complex things that can be done with this. So, but this is everything that people should know, and then there will be different possibilities. Maybe we'll release a problem sheet specifically on combinatorics, which will contain permutation, while you have to count the things. Okay, and that will be a bit advanced where you have to think a lot. And if I see anytime anybody using formulas directly and not thinking from the first principles, okay, that person might get killed by my hands. You should give me the first principles thinking idea. Okay, this is what I have done, this is how do I think. Okay, so again, coming to resort the binomial theorem, which we derived in DeepSeek paper. So if this x plus y to the power n, this is a combinatorial problem. Now you have to fill basically these places. If I say x plus y whole square, this is equal to x square plus y square plus 2ab. So yeah, so the point now is you basically just take two terms. You take these two terms and you sum them up. So this can be expanded in n places. If this is n, this n places. Now there are two possibilities. You can either take x or y. Two possibilities: x or y. Okay, so how many terms would be there? 2 to the power n. That is short. Why? Because we know it from permutation combination. So here there are two possibilities. 2 to the power n terms. So now you have these 2 to the power n terms, and you have to add them. So you have to summation them. So now how will you do it? You will say x and y. So it will be of form, let's suppose, if you take one x and other will be, let's suppose if you take k of x, this will be n minus k of x, n minus k. So if you take x, let's suppose we have x plus y to the power 5. So if you take y 4 times, you have to take x 1 time. If you take y 5 times, you have to take x 0 times, something like this. That's why I say if you take x k times, okay, in this, because you have to form this to the power n sequence. So if you take this x k times, you have to take the other one n minus k times. Okay, then how many such combination will be possible? Because if you see this, so it was x square plus y square plus xy plus xy. Actually, it was like this. Okay, there were these many number of terms. 2 to the power n, that's 2 to the power 2, that is four terms. And each of the term had these two. Now, if you see these two terms are same, then you club them together. Same thing will happen over here. If you have xk, yn minus k. So how many now combination will be there? Because order won't matter. Xy and yx is similar. So you'll use combinations. That's why you'll say n choose k. That's how you arrive at this binomial theorem. If you have to prove it combinatorially, I just rushed through it, but I hope that you will get through it if you do it on your own. So with this, I'll close the permutation and combinations, and this was the prerequisite probability. I hope now you have a good, strong understanding of what probability lies on, and maybe you have to practice a lot. You have to practice this permutations, combinations, set theory, and the rules of these things. We saw some rule, product rule, and we saw inclusion, exclusion rules. All of these things have to be thoroughly revised, and you have to develop an understanding where you think from the first principles and you land the result. And with this, you have now a very easy path to the probability. So I'll stop the recording here. I'll take questions.